Hey guys, this is Coach Lowe, and we're going to talk a little bit about square roots and simplifying radicals. This is our last section in our review chapter. This is section 9, and then we'll get started on some geometry stuff in the next recording. Woo woo! All right, so a little more review of what we need to be successful in geometry. These are just some little pieces. So just reminders on square roots and simplifying radicals. All right, so when we talk about simplifying radicals, to simplify, there are some things that we need to keep in mind. Number 1, we want no perfect squares left under the radical, except one. And when we say under the radical, a shorter way to say that would just be for me to say in the radicand. That's the part that's under the radical. So radicand, if you hear me say that, that's the number that's underneath the radical. All right, we also want, we don't want any fractions under the radicand, or in the radicand either. Let's see if I can get that where it's supposed to go. We don't want any fractions, so no fractions allowed underneath that radical. So this is the part we're talking about. This is the radicand underneath that radical. All right, so we don't want any fractions there. All right, the next thing is we don't want any radicals or any root, like square roots, cube roots, whatever. We don't want any of those radicals in the denominator. Let's see if I can spell that correctly. There we go. All right, so what does that look like? Well, that means if I have a fraction and a square root underneath, I need to work to get rid of that because that is not going to work. I cannot have a square root or cube root or anything like that in the denominator of a fraction. It is not simplified in that case. All right, so to simplify, we want all of these things to go away. All right, so let's look at this first one. How about simplifying the square root of 48? So my goal is, I see that there's not a fraction, but my goal is to simplify this number. There are perfect squares in here and I want to get them out. So if it's a perfect square, I can take the square root of it and it can come out like the square root of 4 is 2. The square root of 9 is 3. The square root of 25 is 5. You guys know perfect squares. You've been working with those for a long time. All right, so let's make a factor tree. Maybe you did this over the last few years. And so what I'm going to do is I'm just going to break down, this is going to be a prime factorization. I'm going to break down 48 into numbers where I can't break it down anymore. So think of two numbers that multiply to be 48. Maybe you thought of 6 and 8. Maybe you thought of 4 and 12. Maybe you thought of 2 and 24. That's totally fine. You can use any of those. I'm going to start with 6 and 8. So that leaves me with 2 and 3 here because 6 breaks down into 2 times 3. All right, when you get to the ends of these branches, you need to ask yourself if you can break them down anymore. If not, just go ahead and put a circle around them. Those are finished. Those branches are done. All right, so let's come over here to the 8. And 8 is 4 times 2. So can I break down 4 anymore? Yes, I can. So it is not finished, but the 2 is, so I'll go ahead and circle it. Now I'm going to go back and break down the 4 one more time. And 4 is 2 times 2. All right, so I'll go ahead and circle those guys. And now I'm going to make a list of what I have here. So I have a 2, a 3, and then another 2 more 2s, and then another 2 up here. So I'm just taking the things that I circled, not the other numbers, because the numbers that I've circled are the breakdown of the numbers that I didn't circle, so I don't want to repeat everything several times, and it's a different number. So I see that I have 4 2s, so 2 times 2 times 2 times 2, and a 3. All right. That's all underneath the radical. I just renamed 48 into all of those numbers. Okay, now, perfect squares mean a number multiplied by itself. So this is a perfect square because it would be 4, and this is a perfect square. So I know that I can take these out since I have a pair. I'm going to take them outside the radical. Now the 3 has to stay on the inside because it is not part of a pair. So I have a 2 times 2 on the outside and a 3 on the inside, and we know that 2 times 2 is 4. So the square root of 48 simplifies into 4 times the square root of 3. And I'm finished because I look under the radical, look at the radicand, it's a 3. It is not a perfect square. There aren't any fractions in that radicand, and I don't have a denominator, so I don't have to worry about that. All right, let's move on to the next one. All right, let's look at multiplying. All right, so the square root of 6 times the square root of 30. Now, several ways to do this. And I'm going to show you the quickest way, but there are several ways to do it. You could just multiply 6 times 30 and get 180. And then you could do the factor tree and break it down from there. 180 is kind of big, though. So I want to think about these numbers before I just jump in and get started. So let's think about the math here behind it. If I can find 2 6s, then I can take one of them out, right? It would be a perfect square. So let's think about the numbers that make up 30. The numbers that make up 30 are 6 times 5. When I multiply radicals together, I just multiply the numbers underneath the radical. So I multiply the radicands together and stick them all underneath one radical. So when I do that, I see that there are 2 6s, which means I can take a 6 out and the 5 has to stay in because it's just one, it's a single. So if they're in pairs, you can take it out because the square root, 6 times 6 is 36, and 36 is a perfect square, obviously, because it's 6 times 6. So it can come out. 5 has to stay in. All right, number 3. Let's look at this one. This one's a little bit crazy. 28x to the 4th, y to the 5th, z to the 12th, and this is all underneath a radical. So that's the radicand, all underneath it. All right, so now I have numbers and variables. I still want to do the same thing with my number. So I'm going to come over here to the side, and I'm going to do a factor tree with 28. So I'm thinking 4 times 7. 4 is a perfect square, isn't it? Because it's 2 times 2. So there's my prime factorization. I have a pair of 2's and 1 7. The 7 has to stay in, the 2 gets to go out. All right, so the 2's on the outside, 7 is on the inside. Okay, now let's look at our numbers. So I have x to the 4th, which means there are 4 x's. It looks like this if I write it out. So how many groups of 2 do I have? Exactly, 2 groups of 2, right? There's a group of 2 and there's a group of 2. So I have 2 groups of 2. So when I write this on the outside, I write x squared, and there aren't any left over. So maybe you've thought about this for just a second. I can divide 4 by 2, and that tells me how many groups of 2. So y to the 5th, I have 2 groups of 2 and 1 left over. Let me see if I can move that y a little bit over. Come on, Mr. What? No, yep. Okay. So think about this on that y. I have 1, 2, 3, come on y's, go ahead and write for me. 3, 4, 5, and I circle my groups of 2. I can circle 2 groups, but this y right here is all by itself. So it has to stay on the inside. And I really want to move that a little bit. Let me see if I can move this. Give me just a second. A little bit so I can get the z in there. There it goes. Okay, perfect. All right, so now let's look at the z's. I have 12 z's. So if I write out 12 z's, how many groups of 2 would I have? Yeah, 6, exactly. So z to the 6th, I don't have any left over. So that's my answer. 2x squared, y squared, z to the 6th, multiplied by the square root of 7y. By the way, when we say that, there are different ways to say it. 2x squared, y squared, z squared times the square root of 7y is one way to say it. You can say multiplied also, just a little bit longer. All right, what happens if we have a square root in the denominator? So I have 2 more problems for us to look at together. So let's look at the square root in the denominator. So this is number 4. Remember, if you have any questions or you need to back up the video, just pause it, back it up, rewatch. If you need to pause and write down notes, please do so. All right, square root of 49 divided by 16. If you want to pause the video and try this one without me, please do it. All right, so now that you're back, if you tried it, there's a couple of things we can do here. You can split up the radicals into 2 different square roots. This is called the quotient property. It says we can go this way with it or we can put it back the other way. Now when I do this, I see 49 is a perfect square and 16 is a perfect square, so I'm finished. I don't have any radicals anymore. There's nothing in the denominator. Done and done. All right, if you see that from back here and you just want to write 7 over 4 outside the radical, then you can totally skip this step and do that. But this is why you could do that. It splits up into two pieces. All right, last one. What if I have 5 over the square root of 3? Remember, the third thing that we don't want is a radical in the denominator. It is not simplified that way. So to get rid of the radical in the denominator, I have to have a perfect square. Well, I know from just earlier math that when we work with fractions, we can multiply top and bottom by the same number and it doesn't change, like when we're adding fractions and we have to find a common denominator. The same thing will work here with radicals. If I want to get rid of the square root of 3 and I need it to be a perfect square, then let's multiply top and bottom by the square root of 3. In reality, this is a 1, isn't it? Let's see if I can get a highlighter going. I don't think it's going to let me. Nope. Okay, so in reality, this is a 1, and we aren't changing the problem any. So remember, with fractions, we'll multiply straight across. So I have 5 times the square root of 3. And on the bottom, I have the square root of 3 times the square root of 3. All right, so no more cleanup on the top, because the square root of 3 is not a perfect square, so I'll leave that. But what about the bottom? The square root of 3 times the square root of 3 is the square root of 9, which is a perfect square. So I get 5 square roots of 3 over 3. All right, that's it, guys. We'll have some things to do when I see you again. If you have questions, make sure you write those down. You need to rewatch the video or any part of it, please do so. This is Coach Lowe, and I'm out.